So last class we were just starting to introduce this idea of quantum algorithms, and we learned a couple fun tricks for implementing them. So we learned about quantum oracles, and we learned about using ancilla qubits to kind of enact these quantum oracles. So tell me, what is a quantum oracle as we've learned it? In mathematical terms, it's a unitary matrix, right? You can also think about it as a switch statement. Does anybody do programming? So switch statement's something that you're familiar with. So you can think of an oracle as a quantum switch statement. So depending on your input, some prediction about the quantum state, the oracle is going to automatically run a particular operation depending on the input's value. So if we predict heads for a coin flip, the oracle will automatically run like an identity gate. Or if we predict tails, then it will automatically run some pi rotation operation. And so what's interesting about thinking about it like a switch statement in classical computing is that just like switch statements, the programmer has to code it. So that means that whenever you use an oracle in a quantum algorithm, you have to have already figured out what switch statement to use. That's usually done by doing a lot of math beforehand, so it's often mathematicians that develop these oracles, as we'll see some examples of today. And then using the oracles, we have already basically figured out how to map the resultant 0 and 1 output states to our input predictions. So we already know that a measurement with outcome 0 identifies the input prediction heads, and a measurement of outcome 1 identifies the unique input tails. So an important note is that they have to be programmed for the function you want to produce. The other thing that we have to keep in mind is that these oracles have to be able to distinguish our encoded input values without affecting any probabilities. So when we saw our example of the Deutsch-Jozsa algorithm, for example, we used a specific kind of oracle called a phase kickback oracle to ensure that we don't affect the probabilities of the outcomes. So let's talk just a little bit more about this phase kickback oracle, because it's actually super important throughout quantum computing and in most of these very famous algorithms that you'll hear about, like Shor's algorithm and Simon's algorithm and Deutsch-Jozsa, Grover's. They all use phase kickback. So let's think about the simplest case with just 2 qubits. So one important thing that we have to keep in mind for this phase kickback trick to work is that the qubit that will be the target in the control operation, so that's our qubit 1 here, needs to be an eigenvector of the operation. It's kind of trivial for us when we're talking about input states of 0 and 1 and all this, but it's just good to remember, because what we want to achieve with that requirement is that applying our operation to our target qubit doesn't change its state, but only affects its phase. So if we apply the operator to our qubit, maybe it looks something like this. U applied to psi equals e to the I theta psi. So the qubit doesn't change its state, it only affects its phase. So in this example, U is our operation, it's our matrix that's acting on our qubit, and the operator only adds a phase to our qubit. And so the value that the qubit is being multiplied by is the phase that will be kicked back to our control qubit. So let's see how that works. All right, so we have our simple phase kickback quantum circuit here. So our top qubit, it's our control qubit in this scenario. It goes through a Hadamard gate, and the bottom qubit goes through our poly X gate. So you can see that in the qubit. So when we get to this part of the circuit, then our quantum state, we'll call it psi 1. It's 1 over square root of 2 times 0, 1 plus 1, 1. So we get this state because we have an equal superposition of our state 0 and our state 1 for our first qubit. So that's the first numbers here. So that's Q0. And then we sent our second qubit, Q1, through an X gate. So Q1 is always 1. So our combined state is as written. So here's where it gets interesting. So now we're going to send the qubits through this controlled phase gate. That's our oracle in this case. And the control qubit being the top one and the target qubit being the bottom one, the names are kind of counterintuitive because the qubit that ends up changing its phase is actually the control qubit. And remember that when we talk about control here, it's in the sense of when we introduce like controlled NOT gates. A controlled gate acts only when the control qubit is in the 1 state, for example. Our phase rotation is only applied in this case when passing through this gate when it's in the 1 state. So our quantum state after we go through this controlled phase gate is equal to 1 over square root of 2 times 0, 1 plus e to the I pi over 4 times 1, 1. And the reason it's like that is because we only shift the second term because our control qubit is in the 1 state only for that second term, not for the first one. So this kind of gets to what we were talking about earlier. The phase gate was applied to the state 1, 1, but it only adds a phase to the control qubit. So we can kind of separate out the target qubit from this quantum state. So notice the two states aren't entangled. Our control qubit and our target qubit, we can express it like I just did, or we can pull the target qubit state out and express it as a tensor product. So they're not entangled. And that's why this ancilla qubit thing works. So once we've kind of done our thing to our control qubit, we can just forget about the target qubit because it just can be pulled out. So we can visualize the effect of the phase if we use a state vector simulation. So QISE, for example, has tools to do this. So you can put this quantum state into QISE and it will give you these kind of diagrams. So our control qubit, Q0, has a phase rotation. So we went through the Hadamard gate, puts it on the XY plane, and then it shifts it in phase away from X. But our target qubit, Q1, is just in the 1 state without any rotation. So this shows that the phase was kicked back to our Q0 qubit rather than being applied to our Q1 qubit. So this effect is what we wanted to achieve when we applied phase rotation to our top qubit, but the qubit was actually acted on by a phase rotation gate, was the bottom qubit. What's also important to note is that this phase shift that we cause by this phase kickback trick can't actually be measured. right? It's a global phase, so it doesn't affect the measured output. We can visualize it using these like simulators, but when we actually go to measure it, we have an equal probability of states 0 and 1 for qubit 0, and we have 1 for qubit 1. That hasn't changed. All right, so the second algorithm that we want to take a look at is Grover's algorithm, which is a way to speed up an unstructured search problem. So normally, algorithms take inputs and produce outputs. And in some sense, Grover's algorithm can be thought of as working backwards. Say we want a 4. So we want to know what numbers we can add together to get a 4. And so sometimes you'll see Grover's algorithm mentioned in regards to factoring numbers, but that's kind of, this would be a really silly way to do that when you have Shor's algorithm, which we'll talk about. This algorithm is designed to speed up an unstructured search problem quadratically, but it can be applied to lots of other types of algorithms. And the trick that allows it to be useful is something called amplitude amplification, which we'll talk quite a bit about. So if we look at the quantum circuit for Grover's algorithm, what we see is it looks a little bit different than what we've seen before. So we just have a single n-qubit register. Our qubits are all starting in the 0 state, ground state. We apply a Hadamard gate, and so all of our qubits are in a superposition. So we really don't know anything about them. They're an equal probability of being 0 or 1. And then we have our oracle, listed here as a unitary gate again. Again, this is just kind of a Boolean function, and we'll talk specifically about what it does. It's another phase kickback type oracle. And then the next part of the algorithm is something called the diffusion operator, and this is where the amplitude amplification trick happens. So each bit before measurement has a probability of measuring 0 and a probability of measuring 1. And this part of the algorithm takes the highest probabilities and makes them higher. And that's at the expense of the lowest probabilities, which end up being lower. And so we end up with a greater separation in the results, making it easier to find the correct answer. And then the last step of the algorithm is measurement. The probability of measuring the thing you want to measure is really, really high after you go through this amplitude amplification trick. So we'll see what that looks like. All right, so here's the problem. In unstructured search, suppose you're given some large list of items, and among those items is one with some unique property that you want to find. So here in our example, we have a bunch of gray boxes, and we have one red box. We want to find that red box. So to find that marked item using classical computation, we would have to check, on average, n over 2 of these boxes, and maybe in the worst case, all n of them. But on a quantum computer using Grover's algorithm, we can find the marked item in roughly square root of n steps using this amplitude amplification trick. A quadratic speed up is a time saver for finding the marked item in our list. It is a big improvement. And another thing to note about Grover's algorithm is that it does not use the list's internal structure, which makes it generic. And that's why it immediately provides a quadratic speed up for many classical problems. All right, so let's look at the oracle. So we have a database, and it's made up of all possible computational basis states. So if we have 3 qubits, let's say, then our list is the states of those 3 qubits, so all the possible 3-qubit basis states. So if we listed these using a normal digit, it would be the states 0 to state 7. So Grover's algorithm uses oracles that add a negative phase to the solution states. So just like we've seen before, if we apply the oracle U to the quantum state X, then X stays X if X is not equal to the winner W, and it becomes minus X if X equals the winner W. And so just like we've seen before, the oracle, if we wanted to write down an explicit diagonal matrix for what this looks like, we would have this diagonal matrix if the qubit that was our winner, the 101 state in this example, and that one is the one that would be given the -1 sign. So really simple diagonal matrix. And this is what makes Grover's algorithm so powerful, and what makes many algorithms that use the phase kickback so powerful, is how easy it is to convert a problem to an oracle with this sort of form. So there's lots of computational problems in which it's difficult to find a solution, but relatively easy to verify the solution. So for those kinds of problems, we can create a function that takes a proposed solution and returns f of x equals 0 if x is not a solution, and f of x equals 1 for a valid solution. So our oracle could be described another way as u applied to x equals -1 raised to the f of x applied to x. And so that matrix, as we saw last time, would look like this diagonal matrix here, where we just have -1 to the f of x on our diagonal, all the way up to 2n minus 1. Okay, so how does the algorithm work? Before we look at the list of items, we have no idea where the marked item is. And so any guess of its location is as good as any other, which we can express in terms of a uniform superposition. And so we're using the sort of summation form of the uniform superposition here. So my superposition state S is 1 over square root of n times the sum over x up to n minus 1 of x. So if at this point we were to measure in the standard basis x, this superposition would collapse to any one of the basis states with the same probability. And that probability is 1 over 2 to the number of qubits. And our chances of guessing the right value is therefore 1 in 2 to the number of qubits. So on average, we would need to try about 2 to the n times to guess the correct item. And that's no good. All right, so what does amplitude amplification do? This is how the quantum computer significantly enhances the probability. And what the procedure does is it stretches out or amplifies the amplitude of the marked item, and it shrinks the amplitudes of the other items so that measuring the final state will return the marked item with near certainty. And so the algorithm has a really nice geometrical interpretation in terms of 2 reflections, which generate a rotation in a 2-dimensional plane. So the only 2 special states that we need to consider when we're building this construction are the winner, so that's our W state here, and the uniform superposition. So here's our S state here. These 2 vectors span some 2-dimensional plane in our complex n-dimensional space. And they're not quite perpendicular, right? Because our winner occurs in the superposition with an amplitude of 1 over square root of n. And so if we want to think about this, we can introduce an additional state. We can call it S prime. That's in the span of these 2 vectors, and it's perpendicular to W. So we create our state S prime perpendicular to W, and it's basically obtained from our superposition state S by removing W and rescaling. So step one in the amplitude amplification trick is to start out with our uniform superposition S, and the left graphic is kind of showing our starting state. So we have our two-dimensional plane spanned by the perpendicular vectors W and S prime, and that allows us to express our initial state S as a function of that angle theta. So S equals sine theta W plus cosine theta S prime, where theta equals the arcsine of S, the inner product of S and W, which is just the arcsine of 1 over square root of n. So the right-hand graphic is showing us a bar graph of the amplitudes of the state S. Okay, so that's our starting construction. So the next step is to apply the oracle, and the oracle in our case is going to be a reflection. We're going to call it U of F, and we're going to reflect the state S. So geometrically, what we just did is reflect the state S about S prime, and this transformation means that the amplitude in front of our state W becomes negative. And so that's what's shown in the bar graph. And this in turn means that the average amplitude of the superposition is now less than 1 over square root of n. So it's been lowered. And that's kind of indicated by that dashed line. Okay, so that's the first part of the amplitude amplification. So that's the reflection. So now we're going to reflect again. So step 3, we now apply an additional reflection. We're going to call it U of S. And we're going to apply it about the state S. So U of S equals 2 times the outer product of S minus 1. So it's shown in the left-hand graphic. So this transformation maps the state US, UF on S and completes the transformation. So what we did is we started with S, we reflected about S prime, and now we reflect back across the original S. So these 2 reflections that we just did correspond to a rotation. So 2 reflections always correspond to a rotation. And the transformation, US, UF, rotates the initial state S closer to the winner. And the action of reflection, the US reflection in the amplitude bar diagram, can be understood as a reflection about the average amplitude. So since the average amplitude has been lowered in the first reflection, this transformation boosts the negative amplitude of W to roughly 3 times its original value, which, and it does that while decreasing the other amplitudes. And so when we go, so we're sort of at this point where we've kind of magnified W about 3 times relative to its starting amplitude, and the other ones are lowered by a bit. And now we're just going to repeat this cycle of double reflection several times. So we go back to step 2, and we repeat the reflection. And we repeat it until the enhancement of the winning amplitude is big enough. So how much is big enough? So after T steps of doing this kind of reflection back and forth, we've transformed our quantum state into US, UF raised to the T, so we've done it T times. And we want to ask ourselves, how many times do we need to apply the rotation to get our winner sufficiently amplified? It turns out that roughly square root of n rotations is good enough. And that becomes clear when you look at the amplitudes of the state of psi. So the amplitude of W grows sort of linearly with the number of applications. So the amplitude of W kind of goes like T times n to the minus 1/2. And so, yeah, square root of n times is good to ensure that we're basically with certainty we'll find our winner. Okay. So that's it. That's Grover's amplitude amplification. So if we go back all the way to our quantum circuit, so remember, we start with our n-qubit quantum register, we generate a uniform superposition, we apply the oracle to mark one of our items, and then we go through this diffusion operator, which is our amplitude amplification trick. And we're going to apply it square root of n times, roughly, in order to amplify the amplitude of our marked state. And then we're going to measure. Good? All right, so let's talk a little bit about Shor's algorithm. So this is a really tough problem to wrap your head around, and basically all of chapter 10 of Sutter kind of picks apart pieces of this. But what I thought we would do to kind of make it digestible to chemists is to look at a specific example where this has been done on a chemical quantum computer in an NMR. So what is Shor's algorithm? Shor's algorithm basically says that, okay, we know any integer number has some can be decomposed uniquely into a product of primes. Finding the prime factors is a hard problem. And so the basis of most secure public key encryption systems rely on this idea that prime factorization is hard. Does anybody, can anybody give us an intuitive feel for why prime factorization is something that's challenging on a classical computer? I don't know if you guys have read about this. So when I have thought about this problem, this is one way I've thought about it. The biggest number you can represent on a 64-bit classical processor is 2 to the 64 minus 1. And that is a large number. It's, let's see, what is it? 18, 446, 744, 0, 73, 709, 551, 615. I think that's right. That's a large number. So that's like the biggest number a 64-bit computer can hold. And so what if you wanted to factor a number that was bigger than that? Well, then the computer, the processor, can't even hold the number directly. So it has to do all kinds of crazy tricks. You have to program it fancily to deal with bigger numbers. And when you get to much bigger numbers, it's going to be impossible. people say it's impossible. Okay. So the assumption that prime factorization becomes impossible for sufficiently large numbers was challenged in 1995 when Peter Shor proposed a polynomial time quantum algorithm for the factoring problem. And it's probably the best example of how quantum computing has changed folks' perceptions about which problems might be tractable. So there's a really great video on IBM's website that it's a kind of an animated movie, but it's Peter Shor talking. He's just kind of talking about how his mathematical discovery was done, who influenced him. Turns out Simon of Simon's algorithm was kind of like the starting point. Some cool conference exchanges, and yeah, it tells the story about how he kind of came about it. It's only like a 5-minute video, so you guys should check it out. And so, okay, so Peter Shor, he put out his paper in 1995 on Shor's algorithm, and in 2001, Isaac Chuang's team developed a way to actually implement it on a real quantum computer. And so this is a picture of his team actually running the experiments that were reported in the 2001 paper that we'll talk about. And what you'll notice if you've ever gone to take an NMR spectrum in our NMR facility is it looks really familiar. So here's a big NMR spectrometer. Here's some computers. There's a lot more wires than normal because they have to really, they had to design some very complex circuitry to be able to orchestrate 300 pulse sequences to get this to work. So let's walk through the problem. Okay, so what is the problem? The problem is we want to find the prime factors of some integer n. The integer n that Chuang chose is a pretty small one. It's 15. What are the prime factors of 15? 3 and 5. We don't need a quantum computer for that, but the point stands. Shor's algorithm works by using a quantum computer to quickly determine the period of a function f of x equals a to the x mod n. So what is this? This is the remainder of a to the x divided by n. And here a is randomly chosen to be some small number with no factors in common with n. And this is done for 2 to the little n values of x in parallel. So this is the quantum circuit that they designed. So here's our n-qubit register. Hadamard gate puts everything into superposition. Here's our ancilla qubit. And we're going to, our oracle here is going to be this function that I just described, this find the remainder of a to the x divided by n. So for n equals 15, we can pick a equals 2, 7, 8, or 13, and we find that a to the 4th mod 15 equals 1. And from this you can conclude that a to the 2 to the k mod n equals 1 for some k greater than or equal to 2. And so in this case, the function f of x simplifies to multiplications. And then you can look at the other values of a. So if a equals 4, 11, or 14, then a to the 2 mod 15 equals 1. And so only some two numbers that you're multiplying well, here, the two numbers that you're multiplying are x0 and x1, and here we only care about x0. And so what this kind of analysis does, and I didn't articulate it super well, what this is telling us is that we only really need 2 qubits in our first register. Because we can kind of group the possibilities into 2. They ended up using 3 because they wanted more robustness. And then for the second register, they could decide how many qubits they wanted by just looking at the log base 2 of 15, which is 4. So 4 qubits and 2 qubits, but they added 1. So they're saying that they need 7 qubits to run this experiment and have it work to some high degree of fidelity. So the 4 qubits, this is what's holding our function f of x. And the other qubits are sort of our register number 1. So the question is, what does their quantum computer look like? And the thing that I find so fun when you read this paper is they're like, oh, we had to devise, a molecule that had never been made before. And it's not a very fancy molecule. So it's an iron with a pentyl group, 2 carbonyls, and then a butadiene. But the butadiene is kind of special because we have 2 C13 nuclei and then a bunch of fluorines. So the qubits in this is the quantum computer. The qubits are these 2 C13 labeled carbons and the 5 fluorines. Okay, so we have 5 19F nuclei. And we have 2 13C nuclei. All 7 spins in this system, what's kind of special about it is that they're very nicely separated in frequency, and they interact pairwise via J coupling. Okay, so what they did was to design a quantum circuit using 300 spin selective radio frequency pulses separated by time intervals. So you can imagine these pulse sequences being a lot like what we saw for the Hahn echo. So 90, 180, 90, just it's that kind of sequence. It's nothing super more fancy than that, but there's a lot of them because they're trying to separately pulse each of these nuclei separately and get them to kind of talk to each other in different ways. And so the pulse sequence is designed so that the resulting transformation of the spin states corresponds to the computational steps in the algorithm. And experimentally, the spins begin in thermal equilibrium, right? So we're in an NMR machine. The solution is at room temperature. You have many molecules in solution. It's not just one molecule. And all of the spins are wherever they are. So you just have a statistical mixture of zeros and ones. So they use temporal averaging to get the 7 spin effective pure state. And you can see sort of in this top example, this is the thermal equilibrium spectra. So you can see all the beautiful coupling between the spin states. So this is spin 1, so it's our fluorine up here in the upper left. Spin 2, this fluorine on the right, and spin 3, the fluorine at the far side. Okay? So these are fluorine 19F NMR spectra. So they did this time averaging to get the experimental spectra for the effective pure ground state. I don't have the plot for those on here, but it's basically just one line for each of the spins. So you can kind of deconvolute all the coupling by kind of setting your pulse sequences exactly right so that you have just one of your spins up. And everything else is just random. And so then they kind of orchestrate their pulse sequence so that they complete the A equals 11 case. And this is the result. So the result is that they have qubits 1 and 2 in the 0 state. So their lines are positive going in the NMR spectrum. And then qubit 3 is in an equal mixture of 0 and 1. So you get sort of a positive signal and a negative signal. And this top line is the simulation of what they expected to get. This is the actual data. And then this is a simulation that adds some sort of random decoherence to the system. So they can kind of say that the answer they got is what they expected plus some noise. All right, so seeing this outcome, so they determined that the first register, so their first 3 qubits, are in a mixture of 0, 0, 0 and 1, 0, 0. And that allows them to determine that the periodicity in the amplitude is 4, which allows them to get the greatest common denominators for 11, for the A equals 11 case, and find that the prime factors are 3 and 5 for n equals 15 and A equals 11. It's a pretty cool experiment. It's very, very complicated. When you actually look at their pulse sequences, it's wild. And this is the easiest case. This data shows the outcome for this A equals 11 case is kind of the easy system. They also, in the paper, do A equals 7, much more complicated. The overall circuit is the same, but like the general circuit is the same, but how they actually get it to do the A to the x mod n part requires a lot more work. But they were able to do both. The noise in the second experiment for the A equals 7 is more, but it's, yeah, pretty cool. So this was like a really big deal in the field 20 years ago. The first time 15 had been factored on an actual quantum computer. It was done in a very reasonable amount of time, and it gives people hope that this is actually something that can be realistically applied in general. These kinds of quantum computers, these molecules, aren't necessarily scalable to things much bigger than, a dozen qubits, but you can kind of see the idea. So that's it. You should read this paper.